Perfect. So thank you so much for inviting me to this session. So my talk is also about hyperparameters and Bayesian inverse problems. And I'm kind of taking the perspective of how we could calibrate hyperparameters or hierarchical parameters in kind of consistently. And so this is joint work with these two fellows, Matt Dunlop from New York University and Andrew Stewart from Caltech. And what I'm going to talk about is related to our joint paper that appeared just earlier this year on this topic. And so just to set the stage, so we consider here linear inverse problems, linear Bayesian inverse problems. Y is my observation, A is my forward map. I'm thinking about kind of my domains as separable Hilbert spaces, and then I have some random noise. And for simplicity, I assume that I have this sort of white noise statistics in my noise here. And I know everybody listening now is familiar with Bayesian inverse problem, but just to set the notation. So my prior here is mu naught, and likelihood is then given in this construction as a Gaussian measure. AU is the mean, and this white noise statistics gives me the covariance, and those together give me a posterior measure. And as we all know, the posterior in this case is absolutely continuous with respect to the prior according to these equations. So let me kind of go through three concepts that kind of relate to what I'm going to talk about with respect to hierarchical parameters. So first of all, map estimators. So map estimators are basically just the mode of the posterior distribution. So in finite dimensional settings, the point that yields the kind of highest probability. And you can generalize this concept to non-parametric cases, non-parametric settings, and there's a maybe the original definition goes to Matérn and others in 2013, where they defined the non-parametric map as some sort of limit of limit, or somehow a point that somehow scales well in the limit of small ball probabilities. So the posterior measure around small balls around a map estimator over in the limit kind of attains the highest mass around itself. And so that sort of point is a map estimator in their definition. Well, I mean, you can approach this from a little bit different perspectives. We did some work on kind of variational formulation of that map estimator, then also a little bit generalization to this approach, and there's, you know, maybe not the last word has been said about how to actually define the map estimator, but the main point in all of these definitions is that you want to have something that connects the map estimator to a variational problem, and that's the positive side of map estimators, that they are fast to compute because they relate to a variational problem. And often they can be analytically studied. So another topic is Matérn fields. So there were already a couple of talks mentioning Matérn fields, so just going through quickly. So Matérn fields are covariance functions that are Gaussian fields with covariance functions defined as here, and you have a couple of parameters here worth to point out. So sigma squared is the variance of the field, L is the length scale as in the previous talk, and then nu here is my regularity parameter that kind of expresses the smoothness of the samples from such Gaussian field. So basically, somehow the samples in this case will poses up to new fractional weak derivatives almost surely. So 2 points how they could be defined. So if you have if your domain is the whole RD, then you can kind of find, or you can kind of give an equivalent definition via the via kind of SPDEs. So in that case, the covariance function is the Green's function of this fractional differential operator. And on the other hand, if you're on bounded domain, then and you have suitable eigenbasis that kind of diagonalizes the Laplace operator, then you can write it write the covariance in this basis and write the covariance operator that has the following eigenvalues. So they are very widely studied Gaussian priors because they can be tuned up to the applications at hand. Okay, and then finally, third concept that I'll mention shortly is what is consistency. So now suppose that our data is generated by some ground truth that I call U dagger. So in that case, I know exactly that my data has certain type of or somehow has some kind of true distribution that I will call with this probability measure here, likelihood measure. And so suppose my posterior is now given, the Bayesian posterior is given by this quantity here. So what happens when the noise goes to 0? So are we kind of, with the Bayes method, are we kind of approximating the ground truth, which are we somehow getting closer to the ground truth? And this is often, or this is the question of posterior consistency. And then if you want to go further than just ask, you know, kind of somehow existence of, or somehow whether this consistency holds, you study posterior contraction rates, and those are defined in the following sense, so that epsilon n is the posterior contraction rate at this ground truth if for any constant m large enough, you have the following convergence to 1, so that as noise goes to 0, this random probability measure, or somehow random probability goes to 1. And these are of course, these are well-studied concepts and a good reference on general Bayesian statics. Non-parametric statistics is, for example, this recent book by Kosa and Vadebart, where you can find a lot of information about these topics. So, but I wanted to talk about hierarchical priors, and let's first of all let's set the notation also for that. So let's denote my hierarchical parameters by theta with the domain capital theta, and here we assume that the dimension of this domain is finite. And so we assume that phi is distributed according to this, so the density is some rho naught, and then the full. Then I will study Gaussian prior distributions that are defined according to this joint distribution. Okay, and now under such a hierarchical prior, my posterior takes this following form. So now the posterior is also dependent on the hierarchical parameters, and that's becomes visible here in the prior. And what does consistency mean for hierarchical priors? Well, there's a paper, pretty recent paper by Knapik and others that study Bayesian procedures for adaptive inference in inverse problems. And so their take on this topic is that the data is generated by some ground truth U dagger, where U dagger somehow implicitly characterizes, so in their case, it's kind of smoothness parameter, which is hierarchical. And so U dagger implicitly characterizes the true hierarchical parameter. So you are still going for consistency in terms of U dagger, but simultaneously you kind of discover what the ground truth theta dagger is. And we take a little bit different perspective. So we assume that the data is generated by some ground truth hierarchical parameter. So I'm thinking I'm doing a lot of imaging in atmosphere, and so for example, the parameter that I'm often interested in, refractive index in the atmosphere, it's driven by obviously like turbulence and Navier-Stokes, and you know there are many parameters there in the flow models that need to be calibrated. And while it is important for me, of course, to recover the true refractive index in the atmosphere, simultaneously it's beneficial to also recover the parameters that are driving the stochastic process of turbulence. And so we are asking that, can we have this sort of, let's say, dirty scheme of recovering these hierarchical parameters consistently as noise go to zero? So or do the map estimators recover the true hierarchical parameters? And so what I will do next, I will consider our linear problem, I will discretize them, and I will study the asymptotics of those map estimators as noise goes to zero, and then I will kind of figure out what is a suitable rate of discretization in terms of taking the noise to zero. And before going into that, let me just mention that map estimator, the main critique may be to using a map estimator. While it's fast, it's also dependent on parameterization. So it's of interest to understand whether kind of reparametrization affects this situation or these convergence properties. And a typical reparametrization in this case, in our problem, is to consider a transformation described here, so that you kind of rewrite our pair U and theta as two independent parameters, psi and, well, theta. This is the hierarchical parameter in the following with the following transformation. So instead of looking at an equation y equals AU plus theta U, you write A and square root of the covariance operator and psi being just white noise. And so with this transformation, this product here has the same statistics as U, and therefore you end up actually with a nonlinear problem with this new parameterization. And why this is interesting is that, well, the posterior is parameterization invariant. So if you figure out the posterior in this case, you can always go back with the transformation. You have the right posterior, Bayesian posterior. Also, MCMC, as most of you know, MCMC can be implemented in dimension robust ways under this parameterization. So that's very it's very tempting to do this reparametrization. However, the map estimators are not parameterization invariant, and therefore we end up with this parameterization. We end up with inherently different map estimator than before. Okay, And so map estimators are somehow minimize so-called Onsager-Machlup functions or energy functions as you like. And for this centered, so the original parameterization, we have the following form. So we have the kind of cost functional here, and then a term coming from the prior, and then due to the hyper parameter, we get this log term because the somehow the normalization of the prior now depends on our hierarchical parameter, so therefore you get this log determinant parameter, and then there's also the density of the hyperparameter. And now if you make that transformation to this non-centered world, then the same Onsager-Machlup functional is basically very much similar, except you are missing the log determinant term. So we are the main question here is, does that affect at all? So I will, throughout the rest of the talk, I will carry out like somehow both of these parametrizations, but the only difference is basically this one small term that is missing. Well, it's not small in the sense of how to solve it fast, but it's small in terms of at least notation. So I will basically postulate most of the results for this centered parameterization, and then kind of mention that what actually you get for the non-centered one. Okay, so with the reverse transformation, actually, so you see that the only difference is this log determinant term. So okay, and for simplicity, I have here only Rn as my domain, but you can check the paper for the non-parametric version. So what we do here is we go from these functionals IC and INC to what we call capital J, where we actually optimize IC with respect to some fixed theta. And so we get kind of get rid of the parameter u and only consider kind of this minimization problem in terms of theta. And in this linear setting, you can obviously find the minimizer explicitly, and then you can go forward and kind of start to consider optimization of this functional JC. Okay, and to actually get some results, let's make some simplification. So we assume that we have kind of diagonality in this problem structure. So A star A and the family of prior covariances are assumed to be strictly positive, and that they can be they are diagonal visible simultaneously with some fixed orthonormal basis. So let us denote the eigenvalues and by a small aj and mu j. And what follows now is that I just I use this construction that I have. I choose another basis, and writing things in that basis actually gives me a diagonal problem, right? So every dimension described here by J becomes now independent. So my data can be considered as inner products of the original data vector with these new basis elements, and this data element is now given by this formula. And now implementing that, or somehow putting that together with the functional J that we constructed. So still I'm keeping uj here, so the I will get the diagonal version of that functional is given here. And now if we actually solve J, we get closer to this formula. So here is the data points. Now what I have added, I will describe in a second why. I have added a constant basically. So I have multiplied these functionals by 1 over capital N, and then I have added here a constant, so you can, so the log of minus log of this mu j at the ground truth hyperparameter. And why I do that is that because I'm only considering the convergence of the optimizers, the map estimators. So I'm not actually worried about the values of these functionals, but just what happens to these minimizers. And of course, these sort of transformations don't change that behavior. And so now recall that we have this frequentist assumption of the data being generated by some ground truth hierarchical parameter. So that means that my data points are coincide in distribution with the following quantity. So Aj were the eigenvalues of this A operator. Here's the eigenvalues of the prior covariance, and then my noise level. And psi j's are IID, white noise. And by plugging that into the formula, I get here. So now we are getting closer to actually saying that what happens when n goes to, or somehow we are getting closer to actually studying this balance between this rising this capital N and letting gamma go to 0. So here's the same formula. So what I want to happen next is that I want that at the limit these quantities go to 1. So I'm kind of sorry, not 1, but go close to the close to mu j at theta dagger divided by mu j of dagger. So I want this gamma squared divided by aj squared to vanish, so that with the strong law of large numbers, these IID numbers will kind of average out, and I will get some constant factor popping up here. So the same one as here. And so to do that, I need to make a couple of assumptions. So I assume that in addition of being finite dimensional, my hierarchical parameter has a compact domain, and then I need some regularity for these mappings. So I want this to go to that quantity. So I need these to have a certain regularity that I'm not going into detail here. And on top of that, as I mentioned earlier, I want this to get that convergence of this quantity. I need certain rate of increasing n with respect to gamma, and that should be such that the minimum over all j up to my cutoff number capital N, such that this quantity goes to 0 as n goes to infinity. And finally, the fourth assumption here is identifiability, which means that how have I parametricized my prior? And for that, I need to understand how this limit behaves. So if I look at this fraction at the limit as j goes to infinity, I need it to exist, obviously, for all hyperparameters or the values of theta, but also as I hope to converge to this g minus log g quantity, I need to know that there's a minimizer for that. And so I need to assume that this is lower semi-continuous, and furthermore, actually, if you have a function like this, so x minus log x, it's minimized at 1. So then I need to know that so at the minimizer, I'm actually at the ground truth. Okay, and so our theorem described in that paper is saying that if you do all that under these assumptions that we made, actually the centered the the map estimator in the centered parametrization of the hyperprior converges to ground truth in probability. And furthermore, if we have if this quantity has a unique minimizer for any ground truth, unique minimizer theta star, then actually the non-centered map estimator converges to that minimizer. So that's actually a negative result. It is showing that in the non-centered version things go wrong, because if I have some unique minimizer that happens to be something else than the ground truth, then I don't recover that ground truth at all. But unfortunately, I mean, due to the time, I can't go to much details here with the proof, but it's more like making kind of stochastic version of gamma convergence type of result here to happen. And let me just show one example how this could be used. So if we go back to this Matérn field that I described in the beginning and look at the bounded domain version where I have this eigenvalue decomposition. So if I look what my function g is in that case, it's given by this quantity here, and the condition that I was saying is that that g coincides with 1 if and only if my hierarchical parameter, the value of my hierarchical parameter coincides with the ground truth. So that means actually that happens in a kind of manifold. If I only consider variance and the length scale, it happens in a manifold of those parameters. So when this equation holds. So in fact, I can't recover uniquely. That's saying that I can't recover uniquely both variance and length scale, but instead I have to kind of look at a parametrization, a quantity like this that I can then recover uniquely. Well, let me not go into details, but that's something to be expected. I mean, because if you on this manifold, actually the measures are absolutely continuous with respect to each other, or the prior is absolutely continuous with respect to each other, and you can't recover or you can't identify the right measure. And then let's look at a small deblurring, simple deblurring toy example. So let's say we are on this domain from 0 to 1. Let's make cosine Fourier basis there and assume that I have the following diagonal operator. So approximately looking at inverse Laplacian with appropriate boundary conditions. Then I make certain prior choose certain prior parameters here, length scale and the variance 1 and certain smoothness. So this actually requires, if we go back and look what sort of rate it requires, is that that in order to get convergence, n should go to 0 to go to infinity at the rate of noise level to the power of something which is let's say -1 over W, where W is over 4. Well, what happens in this case? So here's pictures where we have plotted the objective functional, so that J functional that I was describing earlier. So here are those plots for on the y-axis we have variance, and on the standard deviation, and on the x-axis we have inverse length scale. And so we are looking for the minimizers of these functionals as n goes larger and larger. And here is the kind of the ground truth somehow parametrization. And as you see, as n goes to infinity, the blue curve, which is kind of the minimizing somehow manifold on this picture, is getting closer and closer to the ground truth. And this yellow, which is then the global minimizer, isn't actually getting to the right place, which would be here. So both quantities being 1, which just tells that this is in terms of that identification is non-unique. That you can't recover the exact point, but you can recover somehow the manifold where which parameters are minimizing. And so also with respect to the rate, so here you see that what happens to the error rate. So in fact, if you increase noise slower, let me see that way around. So if you decrease noise slower than that 4, then actually your error is not decreasing. Whereas if you do the correct scaling, something that is larger than 4, then you will get decreasing error rate. And that's it for this talk. So some conclusions. So the true hierarchical parameters can be recovered by map estimator, but not for any parameterization. So some consideration need to be taken. And unlike sampling method, actually the centered parameterization here was preferable. And now you might ask, I mean, why don't you do it by empirical? Why don't you kind of calibrate this problem by looking at empirical estimates to the hierarchical parameter? And that's a good point. Maybe in this linear case, that might be the weapon of choice somehow. But if you look at nonlinear problems, or if you have more complicated prior terms, I don't know if that's any more feasible. And so this map estimator business then kind of, this is kind of first step towards studying map estimators also in those cases, because here looking at these variational problems and studying them are kind of conceptually easier. And so I think with that I can end my talk, and if you want to read more, there's the reference to our paper. So thank you so much.